Okay, well, thank you so much for that brief introduction, Constantine. And I'm very grateful to all the organizers for inviting me back, despite the talk I gave last time. So this is going to be a series of what I wanted to be 3 stories, but it'll end up being 2. This is what happens when you ask me for an abstract, 3 months before the talk. I send some abstract and then reality catches up with me. Okay, so this is basically a talk about links, and links defined in the technical sense involving stratified spaces and all that, but I'll define all of this carefully. So let's get started. So the hero is going to be the link of a stratum, and what that means is we need to sort of define what a singular space is. So hang on, this is again misbehaving. Okay, good. So here's a simple property of manifolds, smooth manifolds. If you take 2 distinct points, P and Q, well, maybe that's the same point, but 2 points, P and Q on a manifold, as long as it's connected, you're guaranteed to find a path on that manifold that takes P to Q. And in fact, you can exploit that path to produce a diffeomorphism that sends P to Q. I found this result in topology from a differentiable viewpoint by Milner, and in pure like Milner fashion, the proof is really delightful. So I thought I'd share a few pictures with you. So first thing to do is check that you can send the origin to any point in the unit ball, which you can with a vector field. All you need is a function that sort of decays radially as you leave the unit ball, and then you can point it in any direction you like, generate a nice vector field, and check that the property holds the ball. And once it holds in the ball, you put any Riemannian metric you like on your smooth manifold. Take a path from your point P to point Q, cover it with balls, and then exploit the fact that you know that this is true. So there's the compactness gives you finitely many times you have to do some dance within a ball, and so you can find, not only can you find a diffeomorphism, it's in fact isotopic to the identity, for those who know what that means, and it doesn't move anything outside a little tube around this path, and you could just be constant away from this path. So for those who like group theory, this is a fancy way of saying that the fancy way of saying this is that the group of diffeomorphisms acts transitively. And a less fancy way is that you take a point, you attack it with every possible diffeomorphism that you can find, and it turns out that the image of that point, the orbit of that point under the diffeomorphism group, gives you all of them. So there's a single orbit. Okay, so this is a really, really nice property. And in fact, the quest for singular spaces begins with trying to recreate this miracle for spaces that are not manifolds. So maybe if you tried to come up with a definition of a good definition of singular space, you would have a filtered topological space at the very least, so that filtered by closed subsets, so that you require the successive differences to be smooth manifolds. And then you've seen these before. We've seen lots of these, at least in this workshop. So here's x0 is just a bunch of points. X1 is a bunch of, when the difference between x1 and x0 is just a bunch of open lines, edges. And then the difference between x2 and x1 is just a bunch of open 2 simplices, and so on. So we've built things like this before. So just, at each step, you're adding a manifold. And of course, for a simplicial complex, you're adding very nice manifolds, but that doesn't have to be the case in general. Okay, so a filtered diffeomorphism is going to be a homeomorphism of your filtered topological space X, whose restriction to each I manifold piece is smooth. And this clearly forms a group. I mean, by definition, everything is invertible. And so our goal is to add conditions to these successive differences so that you recover this transitive action of this the filtered diffeomorphism group, except you know for a fact that you're not going to be able to get things transitive outside a single smooth connected component. So you want this thing to act transitively whenever you have two different points lying in the same connected component of an MI. You want a diffeomorphism of the whole thing that'll send one point to the other within that connected component. So that's where the quest for singular spaces begins. And I think hopefully most people have heard of the fact that this the correct definition of a singular space by just about any metric was given by Whitney, who was looking at analytic varieties. And I think the paper is called Tangents to an Analytic Variety from sometime in the 60s, is my guess. And okay, so you have all the setup from before, and here's the additional condition you want. So you take a deep breath. All right, everyone ready? Okay, so for each pair of strata, so those are these connected components of the ith piece, the ith successive difference, take any point in one of the strata. Now take a sequence, a pair of sequences, one in sigma, that was the first stratum, one in tau, which is the other stratum that contains y. Both these sequences should converge to y. So that's still part of the hypotheses. Now, if the lines, imagine you're embedded in Rn, so you actually have a notion of lines. If the lines joining x to y, the ith x to the ith y, converge to some limiting line, and the tangent planes, because tau is a smooth manifold, if the tangent planes converge to some limiting tangent plane, then this line has to lie in the plane T. Now, this is entirely too much to absorb without a picture. So here's a picture. This is called Whitney's umbrella. And what you see is it's a line, and then there's a parabolic thing circling around it that comes down to 0, and then there are two flaps extending outside. So so in terms of this definition, the point where the parabola just becomes tangent to the line is sort of special, in the sense that if you take the sequence of points converging to it from above, so along the two-dimensional piece, and the sequence of points converging along the line, they both hit. Now, each time you draw the ith line, it's vertical, but the tangent planes, as you converge to that point, become horizontal. And of course, the vertical line does not sit on the horizontal plane, which means that that point, by this definition, the pair consisting of that point and the red bit, the two stratum, does not satisfy Whitney's condition B. So that point would have to be a separate stratum. It is not allowed to be grouped with the line, even though if you took away all the red two-dimensional stuff, what's left is just a line that looks perfectly nice and smooth, right? You shouldn't have to separate that into two different pieces. It's the nicest, smoothest manifold you'd find on the planet. So, so that's the sort of subtlety that you have to worry not just about what's happening along the line you're at, but along any higher direction coming from these higher dimensional strata. So condition B implies this transitivity property that we wanted on each stratum. And it's not obvious to me at all why this should be the case, but it's a theorem, and I think the proof goes back to work by Thom and Mather. Okay, so now we're ready for the main definitions. Take one of these I-dimensional strata of a Whitney stratified space, take any point on that stratum, and because we've sort of lazily embedded the space in Rn, we can find a plane, a linear space of dimension n minus I that cuts that stratum transversely at the point we've chosen. So if you'd like, here's a piece of the Whitney umbrella just along that line, but far away from that deadly point. And if you look at the two-dimensional pieces, there's stuff that goes above, and then there's stuff that comes out. So here's a point P we've chosen basically at random on that line. And so the normal slice to that is exactly what you'd expect. There's a plane transversely cutting that line, and then you look at what part of the space X intersects that plane. And here you get the point P, because we forced our thing to pass through P, and then you get these 4 orange arcs emanating out. And so the link is what you get when you focus on this sort of plane, which was cut transversely through our stratum. Draw a little epsilon ball around the point that is right in the middle, the point P that we chose, and see where the boundary of that ball intersects the orange stuff that survived the intersection. And this is going to be dependent on the stratum you chose. So it'll depend on the line, but it won't depend on the choice P of the point P. It won't depend on the choice of the transverse plane. And it won't depend on epsilon for epsilon sufficiently small. And if you want to get sort of aggressive about what sufficiently small means, basically, for no radius smaller than epsilon should the boundary sphere become tangent to the orange stuff. That's the definition of small enough. Okay, so it is a theorem that you have a stratified homeomorphism. So forget stratified for a second, but a tiny neighborhood around the point P in this ambient Rn intersects this filtered space X in Ri, and I was a dimension of sigma, the stratum containing P, cross the cone on the link. So if you look at this picture over here, the link is 4 points. The cone on the link is exactly the X shape that you would get by coning off 4 points. And then Ri is just R because it was a one-dimensional stratum. So it's like the figure X cross a line. And if you look at the point P, that's exactly what its neighborhood looks like. So good. And this enforces, because the right side does not have anything to do with P, the cone is well-defined independent of P. So it basically guarantees that tiny neighborhoods of points in the same stratum look exactly the same up to homeomorphism. So this is nice. Okay, so this is the hero of this entire talk. I just wanted to set up what the link of the stratum is. Any questions so far? I can't read the chat, so if you want to unmute and ask, this is a great time before I go on to other things.
Who's the villain?
Oh, the villains are coming. The villains are evil pirate captains. Other questions? That was a good question. I will answer more like that. Okay. Well, you can stop me later on. As Constantine says, you all know me apparently, so it's fine. We're all friends here. Okay, so here's the first task of our hero. This is Strange Voyages. So this is a project with Primo Skraba and our 2 postdocs, amazing people, give them jobs, Leon Lamprecht and Barbara Malner. This was funded by the Alan Turing Institute. And let me, instead of sort of giving you a long, detailed description of what the mandate of the task was, I'll just go to show you a bunch of pictures. The reason I'm doing this by slides and not on my iPad is because there's more pictures than I could possibly draw in finite time. So here is trajectory data. What I mean by this is, I think, October 2018. In the Gulf of Mexico, every ship that pinged I am here is now drawn via some trajectory. And we are making no sort of distinctions between cargo boats and little ferries or anything like that. There's, I think, a bit going up the Mississippi. You can see Florida, the Panhandle on the right. And it's a complete mess. And so the job is to figure out whether you can find strange anomalous behavior in trajectory data. Now, I don't know about you, and I don't know how good the resolution of this connection is, but if you could see any part of this picture, it's a mess. It's an unholy, just mess of noodles everywhere. And then figuring out, I mean, there are parts close to the coast where you could basically do anything, and I wouldn't know by looking at a picture like this. I mean, you could have written a rude message out on your trajectory, and I wouldn't be able to read it just because there's so much happening.
How did they go across land?
How do they go across the land? Excellent question. So this is what's called AIS data, and I have, again, persistently forgotten what those three letters stand for, but if you search Google for AIS data, you'll know. And what happens is sometimes ships sort of turn off their transponders, and this
and they go
program
around.
just does linear interpolation, and it doesn't know that you went, assumingly. Some of these are just terrible. I mean, there's clearly people who think that they're, I don't know, maybe it's like James Bond turned into a submarine at the edge of the coast or something, and then just went into the water. Anyhow, so we're supposed to find anomalous trajectories, and with not much of a description of what anomalous means. And that's sort of the problem, right? I mean, in this day and age, what you'd like to do morally is to just train a giant neural network over years and years to study all sorts of trajectories and decide what's strange and what's not. Unfortunately, this is impossible for the reason that we don't have good labeled data of which trajectories were normal and which ones were not. So there's no sort of way to train these giant neural networks. And so I guess one of the things we should do is sort of produce either synthetic or natural data set where somebody did something they weren't supposed to do. Okay, so I don't really know what you would do if you were confronting this data set and we're trying to solve this problem. But here's what we did. I mean, the first thing to do is do some basic zeroth order filtering. And so here it is. So first cut down from a whole October month to just the first week of October in 2018. Now this is looking slightly better. Maybe if you squint at it, you start to see some structure. You will see the big ports because things are exploding out of them. Maybe towards the right, it's easy. You see a lot of people sailing around the panhandle. And if you really start to zoom in, there are a few very interesting points where ships go straight to that point and diverge. So maybe towards the northwest of the picture that's here. Anyway, so that's one level of filtering. And then the other level of filtering would be to restrict to a kind of ships that would make sort of reasonable long journeys. So this is only restricting to cargo ships. So now what you see on the right is only cargo ships, only for the first week of October 2018. And now I see a graph that's embedded on this patch of the Gulf of Mexico. And the presumption is that this is what a normal week's worth of ships should look like. Hopefully, cargo ships at the very least. So there are vertices. So those are where these major shipping lanes intersect, and then there are these just lanes themselves away from the vertices. And so the question is, can you learn what this graph is from some given historical data, and then compute? If someone gives you a new trajectory, you plot it out here, look at how far away it is from this graph of what most people did, and say, hey, this was pretty far away, so at least spatially you look like you were in places that no other cargo ship has gone for this week. Questions about this? No. Okay, good. So so the idea is to exploit what we've learned about links. So the links around points that live on these highways far away from the intersections are very different from the links at intersections. Here's a typical, you're just going straight across in your own shipping lane. Maybe you have a friend, but they're going parallel, maybe in the opposite direction, but this is fine. And here is where you had one of these interesting points where things came apart and then came together and went apart. So you can tell by the way these trajectories intersect these boundary circles that something very different is happening. So the goal is to figure out what these intersection points are so we can learn the structure of the embedded graph. And so take a grid that sort of nicely covers the entire maritime region we're interested in. And around each grid point, take a tiny little circle of, I don't know how many, this is to be determined, and examine where all the trajectories cross that circle. So this is a set of nearby trajectories crossing that point. And just compute, I mean, this is points living on a circle. There's not much to do with higher dimensional homology. So we're just looking at the zeroth, the zeroth barcode. So write Li for the length of the longest bar and define this ratio, which is the difference of adjacent bars normalized by the length of the ith bar. And the putative degree of P is this weird formula, which I'm not going to read out because it's sort of painful. The way to arrive at this formula, if you haven't ever seen this problem before, is to start with the unit circle and then draw the roots of unity on it. So +1, -1, and then the third roots of unity and the fourth roots of unity, and look at what the barcode is. And so that's sort of the ideal cases with the nicest, both best separated signal, and then imagine that things are a little bit fluctuated from it. Now I'm hiding a lot of details here. We obviously had to do certain filtering by density because one outlier is going to completely ruin this. You have like a very thick highway, 500 trajectories crossing left to right, and then one guy decided to go up and down, and that completely destroys the signal you're looking for. So you have to filter by density, but I'm sort of ignoring that for now. Okay, so now with this degree definition, points of degree bigger than equal to 2 give points on highways and intersections. And if you don't believe me, here are the pictures. So on the left was that filtered thing I gave you at the beginning, which was just cargo ships for 1 week. And those red things are slightly thickened grid points. And hopefully you can see that we have this. So if you plotted just the degree strictly bigger than 2, you would just see the intersection points, all the edges would disappear. So maybe if you can see my mouse, like this point would survive degree strictly bigger than 2. None of these points would survive degree strictly bigger than 2 because they literally look like that picture I drew, a circle with like a straight line going through it, and it's dead. I mean, the persistent degree is 2. Whereas here you have, if you draw a little circle around that point, you will see some interesting behavior. And of course, we're just doing zeroth homology. None of this is very expensive to compute. So there's a baseline framework to compare any new trajectory against. And just to show you what came of this, we found 3 fairly bizarre looking trajectories. And again, I don't know how good the resolution is at your end, but I'll try and show you what they look like. So there's a yellow one, a purple one, and a blue one. So the yellow one is the thing that just kisses the coast on the left. Maybe I can trace it out here if you see this. So this guy, none of the other cargo ships were this close to the coast. So I don't quite know what was happening here. We didn't have a chance to sort of look at them. The blue one, you can't quite see it, but this guy, took this journey in and then came back out. So he did a little loop and then, and same for the red one. This red one went in and then came back out. So none of the other ships went in and then came out. And so this was fairly easy to find in our, I haven't overlaid the graph on this because then you won't be able to see anything except a few of these. Constantine.
Sorry, Vidit, I lost the punchline somewhere. Okay, so you had the previous slide where you had all the trajectories.
Yeah.
And you used that data to find, to identify, say, the intersection, what we call intersection points or straight lines, right?
Right.
Okay, so now I've got a geometry. I've gone from the data to having an understanding of the geometry. Now, how did you then...
So if you look at the pictures on the right,
yes.
The picture on the right, that's our sort of baseline for what we expect to find.
Okay.
Right. And now those were generated by not just every trajectory, but a sufficiently dense, right?
Okay.
So we only considered things on the circle that were sufficiently dense. So if only one ship crossed, we wouldn't consider that a part of the highway.
Okay, so you're talking about how many, okay.
Yeah, so there's a density based, and the density sort of decreases as you go away from the shore, and there's all sorts of stuff I
Yes,
haven't
okay,
told you.
okay.
But if you look at the red picture and now overlay the trajectories of these three guys on it,
But
these three,
they lie on, I mean, the blue one looks like it might lie exactly on, I mean, there is that trajectory that goes up and comes back. I mean, you see the little red thing that's sticking up into the river, right?
yeah.
Isn't that part of that trajectory?
So we're computing the furthest distance from this red to the blue,
Okay,
right? So there are points on here that
I
are
see.
far
Okay,
away
okay.
from anything red.
okay, now I got
If-
it.
Does that make
Each
Do you have a
path,
pointer?
and you measured how far it was from the red grid.
exactly? And
Ah.
these are the ones, like, we drew the histogram and these three sort of lit up like light bulbs. And so
Okay,
there
and
is some
I got-
point on this
that
blue.
was the punchline
Yeah,
I was
yeah.
missing. Got it.
Okay.
Thanks, sorry.
Do you have a pointer or something?
Do I have like this mouse?
Oh, yeah, good. Okay, all right.
Is that it?
Yeah, just like when you, when you say this.
Okay,
this.
okay. All right,
Yeah.
right. Yes,
So
I will try and point more to it, I guess. Okay. Any other questions? Okay, good. All right. So the next bit is a little bit of intersection theory, and this is joined with Martin Helmer, a completely different thing, nothing to do with ships and all of that. So we're,
Sorry,
Oh,
Vidit, because this
go
is,
back.
I'm sorry, this is really interesting.
okay.
So you've given us a really nice principle to do this, which is nice and clean. And then you said, of course, you have to do all sorts of filtering.
Yeah.
How hard? I mean, because if you go back even one slide before, there was all these places where it looks like things get turned on and off, right? I mean, maybe even one slide earlier is even better, right? I mean, there's lots of, or even your no, sorry, go back to the original. Yeah, even here, you see there are whole places where there's kind of zero density. With your eye, you fill in the path. I mean, how systematic is the I don't know what you call data cleaning even, right? I mean, the data processing to get it into this nice idea.
So I think there are three pieces of, I mean, there's lots of filtering, but there's three pieces of super serious filtering that have to happen. One is the fact that, as you can see on the picture on the left, maybe I'll use a pointer for Andy and everyone else. The density near the coast. So to be noticed as a normal behavior near the coast, you have to be. That's a much more serious constraint than what happens far away. So basically, there's a cutoff function, much like Milner's for the disk thing, which basically decays very rapidly as you go away from the shore, and then if you're more than that function dense, then you count as normal behavior. Otherwise, you don't. And so so technically, you could say this is living in a function space, so it's an infinite amount of information. But really, we're just keeping it's a cutoff function basically. So where to cut that off, that is the major parameter there. The second bit is when we look at the circle crossings, what counts as an outlier with respect to the local density of the circles. And there's like a micro radius that we grow out. So if you have no nearest neighbor, for a tenth of the radius of the circle, then we just throw you out. Otherwise, you do clustering based on. So it's just these finicky things. And if I started talking about them, I will send you a link to the preprint when it's done. How's that? And then you can see the list of the filters. But you're absolutely right. If we tried this strategy, even on the picture on the left near the coast, it would be garbage. Like just everything would be filled out. The filtering is a serious pre-processing step without which nothing would work.
Okay.
But
Vidit, can you not only identify anomalous paths, but identify normal paths and the density with which they're taken, so that it wouldn't look quite so messy, but all of these things that are right along the coast and I guess normal would just be one path, right? So you'd say that's a normal.
Yeah, right. So basically the thing is that path would be so thick that within that path you could do donuts and I wouldn't know, just because there's so much else going on there. By doing donuts, I just mean making loops.
Okay. All right.
And I should emphasize, we did not take any higher order, like no velocity, no turning off, your ship in the middle of the scene, none of that. This is just positional information. We could do a lot more with this that we just haven't had time to do yet. Anything else? Okay, well, great. Those were some nice questions. Let me see if I can. Okay, so now we're going to do intersection theory, which means half of you can fall asleep and the other half can wake up, maybe, or ideally everyone stays up for everything. A little bit of setup for what we're going to do. My dream is to do lots of calculations that currently require very, very serious nonlinear algebra, like Grobner bases and ideal eliminations, is computational algebraic geometry, and to replace them with things that you could do if you didn't even have the equations of varieties at your disposal. So I want to give you one simple example of this. So here's the basic thing you would see in a graduate course on algebraic geometry. A projective variety is a zero set of a homogeneous polynomial, or some collection of homogeneous polynomials. So here, everything is happening over the complex numbers to keep life a little bit easier. And so here's one, Z1, Z2 minus Z3 squared is a homogeneous polynomial of degree 2. Its zero set is an algebraic. It's a projective variety. The baby example is a Riemann sphere, and its proper subvarieties are finite unions of points. And I cannot draw accurate pictures for n greater than 1, because the minute you have 2 complex dimensions, that's 4 real dimensions, and that's right out for me. The natural notion of morphism between 2 of these is a rational map. So it's you find an open dense set, and you have a germ of a rational map on the intersection. So these are equal on a dense subset. So 2 varieties are birationally equivalent if there's a rational map with a rational inverse. And this is sort of the in complex projective geometry, this is the sort of equivalence relation you don't want to care about. You want to consider 2 things the same. It's like in homology, it's if 2 cycles are shared, they share a common boundary, or happen to be common boundaries of the same chain, then you sort of want to identify them. So there is a cohomology-like thing that you can define for any complex projective variety, which is just the free abelian group generated by subvarieties, and then you mod out by this nice equivalence relation. Unlike homology or persistent homology, this is not easy to compute. The only examples, sort of, if you knocked out an algebraic variety and I asked you to compute this quotient, this Chow group, it would be difficult. But for complex projective space itself, it's really nice. It's this polynomial ring where you quotient out by degree n plus 1 polynomial. So very nice polynomial ring. And this contains an embedded copy. So you can realize the Chow ring as generated by some sequence of polynomials. So if you write x and y for the classes of, with the brackets for equivalence classes, then they intersect as polynomials. And so the intersections polynomial is the product of the x and y polynomials. And this is all of intersection theory. And there's a special element here called the Segre class, which I'm not going to have time to define. But it becomes a polynomial. And what we're interested in is computing the coefficient of x in the Segre class of xy. This is called the Hilbert-Samuel multiplicity of y along x. Now, I absolutely, for this audience, do not expect you to to love any of these objects that are on the screen or to even be familiar with them, I will give you a much nicer definition of this EXY, which we care about computing, which you can arrive at in a much more geometric way. So the degree of projective variety is the number of points you get by intersecting it with the correct number of planes. So if it is a k-dimensional variety, then you intersect it with k-generic planes and you count the number of points. So for this sphere, you intersect with the plane, you get a circle, intersect with another plane, you get 2 points. So the degree of that sphere is 2. And the miracle, of course, is that this does, unlike for manifold sitting in Rn, this is well defined. A compact manifold in Rn, you just miss, with a far enough away hyperplane. But here you get a well-defined intersection number. Okay, so there is a formula for describing this EXY number that I want to talk about in terms of degrees. So if you know the generating polynomials for the smaller variety X, and they're all degree D homogeneous polynomials, then you can take these linear combinations of them. So take random complex numbers, lambda I, and form lambda I fi, the sums over those. So that's a new family of polynomials. Okay, so it's sort of terrible. But what you notice is that if you set these to 0, then X lies in the 0 set of all of them, right? So if you look at the sum lambda I fi, and you take a point where all the fi are 0, then this linear combination is also 0. So it's just some mess of varieties that all contain the smaller variety X. And now you take the intersection of dim X many general hyperplanes. And so here's a formula that maybe looks a little bit better than the Segre class purely algebraic definition. So at the bottom is a degree of X, which is defined. So everything here is a degree. So there's degree of Y, then there's degree of Y intersect, all bunch of stuff minus X, and then this D, which is the degree of all the polynomials that we needed to define X. Okay, again, not an ideal formula, but the only case in which I want to use this formula is when P, like X is a single point P. In this case, we have a much nicer thing. And let's go to the picture on the right. So you take the point P, that's the central point, and then there's this variety Y sitting around it, intersect with a hyperplane that misses P, like just a generic hyperplane, that's 3. Intersect with a hyperplane that passes through P, and that contains 1 point. And so the degree of, so this EPY is just 3 here. So you take the number of blue points, take the number of red points if you see any, and then subtract 1 from that. So here you just get 3. So it's just the degree of Y minus the degree of Y intersect V minus P, and V is just the intersection of dim Y hyperplanes through P. Okay, so you can use some fairly standard intersection theoretic, just properties of the Segre class really, to say that EXY is equal to EX intersect L, Y intersect L, and L is just dimension X many hyperplanes. So basically you imagine you have X, you sitting inside Y, and then you cut it with the appropriate number of hyperplanes so that X is just a union of points. And Y is itself cut down to some smaller variety, some section of the old Y, so Y intersect L, and that doesn't change the degree. So like if you had this cone and you cut it with the blue plane that goes through that point, then the degree of the point on the plane intersect cone would be the same as the degree of the point on the cone. But the new theorem is that if you had if you took as many hyperplanes as which is any number that's strictly less than the dimension of Y, then EPY is the same as EPY intersect L, which is just saying as long as all those hyperplanes pass through X, sorry, through the point P. Let me sort of say that again because I think it's important. You have a subvariety X living inside a big variety Y. If you cut, let's say X has dimension I, if you attack this y with I hyperplanes, x is just some union of points. That's all that's left in the intersection. But y has just lowered its dimension by I, and it could still be some hideously high dimensional variety. The point is, if you then took one of those finitely many points that x was reduced to, and then further attacked it with the right number of hyperplanes so that you did not exceed the dimension of y, then EPY is EPY intersect L. So as long as your new hyperplanes are not generic in the sense that they all pass through this one special point in X. So, and the proof is not so important. It just follows from that degree-based formula where P is a single point. The upshot is that any of these EXYs can be replaced by EPC, where P is a point and C is a one-dimensional variety. You do not need an arbitrarily high codimension to do this. So this is all I want to say about sections. And so our new purpose in life is to compute this EPC. So it's a degree of a curve minus the degree of curve intersect a single hyperplane through P, except for the fact that you contain P, and so you remove that one point. And now we're ready to do geometry. The key piece of information is Thom's first isotopy lemma, which says if you have a Whitney stratified space and a proper map so that the restriction to each stratum is a submersion, then you have a stratified fiber bundle. Picture, basically, if you look at the fiber over any point that's not the exceptional point that's been marked over here, let me actually, except for this point. So this point's fiber is a single point itself, and this point's fiber is going to be a full circle. That's what I mean. But as you move around, you still see a circle. So it's a fibration with fiber being a circle. And the requirement is that, of course, the derivative has to be surjective here. You restrict to, it's a smooth manifold up top, it's a smooth manifold at the bottom, so the derivative is well defined. So the plan is to find a function that sends P to 0 and satisfies this stratified fiber bundle hypotheses on some small interval, and compare the cardinalities of level sets at 0 and delta for some small delta. And then the thing we want is a difference of the cardinalities with 1 being added because the point P itself is counted in the second intersection and we don't want to count it. So much nicer picture than that is you take an arbitrary non-degenerate direction. All that means is that that direction does not become tangent to any limiting piece of y at the point P, limiting piece of the curve at the point P. And these are dense and they're easy to find. So here is the picture. So C is some curve. I'm lying here because it's I've drawn a one-dimensional picture and it's a one-dimensional complex curve. So the blue stuff should be 2D somehow. P is the point. And now C is just the direction defining the hyperplane that cuts horizontally across the picture. And so you go through P and then you shift a little bit and you go through you do not go through P. And so what is going to happen here, let me get the cursor back, is this hyperplane where pi C, this projection equals delta, is going to cut. It's generic. There's no sort of assumption on it. So this is going to cut in the number of in a number of points. That's the degree of the curve C. By definition, right? It's a one-dimensional object. I cut it with one hyperplane. There are some points, and that's a degree. Now, this bottom plane also cuts in some number of points, which is going to be strictly fewer than the degree because it's not generic. We forced it to pass through P. And the difference in the top intersection and the bottom intersection, except for the fact that we're counting P, is the number to compute. That's EXY. Provided you cut X down to a point P and Y down to this curve C. So that's exactly what I said. We want to compute the difference in cardinalities. And now there's a homological argument. So you have the level set at 0, you have the level set at delta, and then you have the level set over the whole interval 0 to delta. And now you do just basic vector field stuff, look at the downward pointing vector field on the interval 0 to delta, lift it because you have Thom's isotopy lemma, so you can lift vector fields because the derivative is surjective. And so the top layer, that has the same homology as the green stuff, right? You can just flow things down into the green stuff, and that's a equivalence. It's in fact the homotopy equivalent. And the other inclusion, well, what's going to happen? Let me again show you. So this point far away from P, there's a unique line up here. There's no way that this is going to branch off into two, whereas over P, you get these two. So all this other inclusion part is saying is that you can localize the deficit to something around P. Away from P, there's going to be a one-to-one correspondence between points that touched at delta and points that touched at Q, points that touched at 0. Okay, so it's a little bit of work, and reducing to the Euler characteristics, you get that the difference of cardinalities is 1 minus something that happens in a tiny ball around P. So phi is the map you get from flowing down, and pi c inverse delta is, of course, the level set over here. So those two circled points at the top, that cardinality is all that matters. The faraway points that don't flow to P do not matter, because they're just going to get counted at the top, counted at the bottom, and then subtract, then it's gone. So this works, all of this works because we have a 0-dimensional space. I mean, the intersection of the top and the intersection of the bottom are both 0. We started with a point on a curve. We wanted to compute a difference of degrees. And we found a nice direction and realized that this Euler characteristic relationship holds, where we have the real part of the projection along C. And phi is just a homotopy inverse to the inclusion. And because you have a 0-dimensional space, its cardinality is the same as the Euler characteristic. And this only depends on a bit near P. And so I just want to end by explaining what this weird space is, phi inverse P intersect pi c inverse delta, and how it depends on these choices of c, delta, and phi. So here's what's really happening in this calculation. When you look at the link of a stratum in a complex analytic space, there's a lovely symmetry. So let me show you. So on the left, this is a real sort of, this could be a graph or something. So it's a stratified space with real strata. And you could have these this 3-point link here. Whereas if you were defining a complex analytic space or a projective variety, this could never happen. Any way you look, there's going to be a sort of rotational symmetry, except along the axes where the orange stuff becomes tangent to the axis. What this means is that if you took exactly the intersection that was defining the link, but instead of looking at the boundary of the ball, you looked at the entire ball and then cut at a hyperplane that just misses a P, you would get a well-defined space. This is called a complex link, and it's used to define things like nearby cycles, but I'm not going to get into that. And so the theorem is the Hilbert-Samuel multiplicity that we wanted to compute, that was this strange object defined by the Segre class, is the Euler characteristic of the complex link of P and C, where C is the intersection of Y with codimension 1 many hyperplanes containing the point P of X. Okay, why did we do all of this? What is the point? The point is that if you want to compute EXY, you do not need the equations of X or Y. You can infer this number without doing any Grobner basis, any sort of hardcore elimination. You don't need the defining polynomials. You just need points sampled from X and Y, these two varieties. So here's an example. So we took an upward parabola, a downward parabola, and a plane, all three of which intersect in a line. And then we tried to build a complex link. And this is now easy. You take, at the line, you just take a plane that cuts across the line, draw a little annulus around the intersection of the plane with the points of Y. And here are 3 different pictures we produced. The EXY for that example is 3. And all that's happening here is that you're getting 3 connected components of points. And none of this required knowledge of the polynomials that generated X or Y. You can just, any clustering algorithm worth its salt is going to look at these and give you 3 clusters. Now, are there times when this goes wrong? Absolutely. It happens when the direction that we choose the C is very close to being tangent to the parabolas of the plane. But most choices give you this lovely decomposition. And then from this, you can figure out the EXY number you wanted without eliminating any ideals in any ring, just by clustering. So this was the goal, was to eliminate the dependence on equations. That's all I have. And so if there are any questions, I'm very happy to answer them. Thank you for listening.
But how do you sample densely from X and Y if you don't know their equations?
Well, here we know there.
If you have an image or something, then you can look at dark spots and sample, but anyway.
So yeah, in this case, we knew the equations, but we only used the equations to generate the points. And then we, obviously at no point after we had produced these points did we access the equations.
But if X and Y are higher dimensional, I guess if you do some of this, you reduce the dimension, but it's not so easy to sample from, sets of equations.
Yeah, it's true. It's not easy to sample from algebraic varieties, but you can, yeah, I don't disagree with that. I think it's certainly a challenging problem to sample. But all I was going for was not having to do Grobner bases on like hideously large, 50 polynomials, 80 degrees. There's no way that you'd actually get anything in the lifespan of the universe.
Are there other questions, comments? Should we give Vidit a round of applause? Oh, you're done, right?
Yeah, I have no more.
Yeah, yeah.
I
No
quit.
music,